So, morning everyone. Looks like most of you found your way back into this room, despite it was a bit warm outside. So we will try to, we also do, steepest gradient descent on our conditions here. So today we have one small ventilator back there, and then tomorrow, we try to get a larger room so that the ventilation, well, the heat we produce is spread over a larger volume. So like try to improve that on a daily basis. So today is what I would call like the core deep learning day in terms of solving models. Yesterday we looked into, or like we repeated what neural nets are, but then we looked into the fundamental building blocks of structural estimation, so like value function iteration, etc., and how you do structural estimation of a model confronted to data. But as I mentioned yesterday, if you use like these classical methods, you suffer. You can get quite far, but you suffer at some point some walls that limits you in terms of richness of your model, of nonlinearity in your model, of heterogeneity in your model at a large, and then also confronting these rich models for data due to a variety of reasons that I will point out. So the program today is essentially all deep learning, right? But essentially what we will show you is in a variety of lectures how you can solve highly nonlinear rich models with a lot of state variables. Both like, the state variables can be representative for like models with a finite amount of agents, but a lot of agents, or actually continuum of agents. And one other thing that Felix will talk about today is also, if you have like rich models with a lot of uncertainty in there. So for instance, in climate models, you want to quantify the models. So like, the model predictions, what parameters are driving the results. So we will, for instance, introduce there a technique from engineering, which is called surrogates. So like, because with neural nets, you can afford a lot of state variables. Why solve a model many times for a particular given set of parameters and do a loop around them? Why not just solve a model once for all endogenous, exogenous states, and all the parameters as additional states as well? And then you have a gigantic lookup table. Then you can do post-processing with that exposed. So this goes into the logic what John Stachurski said. Sometimes it's more efficient to just solve one big problem in one go, because like you can leverage a lot of computational advantages there instead of solve it sequentially, because the sequentially way is not parallelizable. But anyway, so what I will do is I will start with a technique which we call deep equilibrium net, which is co-authored with Marlon Acinovic, which tomorrow will do the pizza and coding session, and Luca Gagau, who is at the University of Zurich. So I will spend quite a fair amount of time to motivate this technique, because I think it also applies to all the, it strictly applies to all the methods that we will see also later today. So what are the computational bottlenecks and how you can get around them. And then I'll try to introduce this deep equilibrium nets in a sequential fashion actually. So I will try to motivate, what is the difference between the typical iterative solution methods, value function iteration, time iteration, what is the difference to deep equilibrium nets. And then I have two simple notebooks that I want to step you through so you can actually see what's going on. They're not tuned in any way, but like they're relatively straightforward to understand. And then there's tuned codes online that you can find, and if you are able to understand how to reformulate these economic models in this way, you can plug them into the solvers that you provide to you also online. But essentially, we will start like with the non-stochastic growth model, just one state variable. It sort of contradicts what I was just saying. Many state variables, and then I come up with a non-stochastic one-dimensional model. But like it illustrates the basic idea very simply, you know, like how you reformulate the recursive problem in an appropriate fashion. Then we extend that model, you know, into stochastic model. So like we had AR1 shocks, because like one of the complications typically is if you have like, you know, exogenous shocks at some point in time, you typically need to compute expectations. You know, so we enrich that model here too. Then we run that, and then once you have built this, you know, this framework, essentially, I will talk you, if you have time, also with an overlapping generation model, which then has like 60 dimensions. You will also find the codes online, and you can solve these type of models still relatively easily on the laptop, which is quite different. Well, global solutions of these models on a laptop, which is quite different than what you're probably used to from grad school. Okay, so let me just, you know, start with some motivational slides. You know, we have heard yesterday from Bertel's talk, and also others, you know, like, you know, from data, like people are different. People with this heterogeneity, right? So if you look, for instance, you know, some are young, some are middle-aged, some are old. I'm not finger pointing here. some are rich and can afford a new Volvo. Some are poor and have to buy the $1 Volvo. You know, that means, you know, like if you write down a model, say for instance, like a pay-as-you-go retirement scheme, you need to take this heterogeneity into account. Then you will also have, like, depending on, you know, where you are in these curves, you know, some of us are borrowing constrained if they want to buy a house, or you know, go to university, some are not. Some of us have liquid assets, illiquid assets, some are hand-to-mouth consumers. So if you want to, as I said, model, say, a retirement, pay-as-you-go retirement scheme in a meaningful fashion, you may want to incorporate all that in your model. So like, if you just assume, okay, we have a different age bins, say, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so it would be 12, you know, age bins. You can say you have here, you know, 10 agents within each age bin, so you have 10 times 120 ages, 10 times 10 times 12, you know, type of agents that you may want to model. I mean, this is a stylized discussion, of course, but you see, then you assume all the agents have probably 2 state variables, so your state space is 240 dimensional. And due to borrowing constraints and all these sort of funky features, your model is nonlinear. So you need a global solution to a very high dimensional object. Typically, what you do is, you know, in the type of overlapping generations model, as you have seen, you know, you would write down the first order conditions, you stack them, so you would have, like, you know, your state variables, so that would be 240 dimensional vector. You would want to approximate, say, a 120 dimensional policy that would be like, say, the tomorrow capital, you know, either the savings or tomorrow's capital. And then, you know, because you have, you know, you will need to have like KKT multipliers. So you have probably another 240, no, yeah, 240 extra, you know, policies you need to keep track. So you have a mapping, say, from 240 to 480. So 480 functions you may want to approximate. But so this is typically solved by writing down the first order conditions. Then you have a nonlinear set of equations. Then you would need to map that on a grid. On each of these grid points, you know, you solve this. Then you have some, you know, function approximator that you fit over that, and, you know, you sequentially iterate on that expression until you converge. Now, of course, like such a high dimensional object, you cannot approximate on a naive Cartesian grid. And why can't you? You know, say if you have in one dimension, so like what John Sikorsky yesterday showed with the value function injection, you would just take a regular grid. So if you have 1, 2, 3, even 4 dimensions, you know, it works, but you suffer the curse of dimensionality. If you have here 10 points, 10 points, so it's 10 to the d. After 4 or 5 dimensions, you're just dead because this thing grows, you know, the number of problems you need to solve, they grow exponentially. Then there, you know, there's some other problems if you go to high dimensions. A lot of models, so there's a ergodic distribution, so like where the model lives, is typically a cube. When you simulate the model, this, you know, I'll get back to that if you simulate the model, this typically looks like, say, a sphere or something like that. Now you can clearly see if you solve a problem on a hypercube, you know, you need, you know, if you remember just mentally, you know, the grid points here, the grid points here, the grid points here. So like this white region you never visit, but you would still solve the model there. It's kind of useless. You would solve it here, here. Why would you care? And this is in 1 or 2, well, in 2 dimensions, you could argue, okay, why bother? You know, it's like 50% of the computation you waste. But you see, if you go to high-dimensional problems, you know, funky things start to happen. So, you know, if you assume that would be a sphere, so the bounding box, because like if you have a grid-based method, of course, if you want to compute the global solution to your problem, the box that contains your model needs always to be bigger than, you know, you simulate, right? So the ratio in 2 dimensions of a sphere, and you know, a very good chosen box, so like you really touch the sphere, that would be 1.2. In 3 dimensions, such a ball is 1/2. So like, you know, essentially, you know, you waste half of the computation. But this ratio is in 100 dimensions. And again, this is probably something that we want to deal with. This is 1 to 10 to the 40. So like you need to solve 10 to the 40 problems to have one, you know, problem solved which is relevant to you. So this is clearly not optimal in any sense. I mean, it's infeasible, clearly, but I'm just saying. So the ratio of the volume of the sphere over the volume of a cube, that goes with 1 over the dimension factorial. So already in 5, 6 dimensions, you know, the space that you're interested in is infinitely smaller compared to a box. And you know, let me just put a bunch of more numbers to make that thing more explicit. So let's assume, so yesterday we have seen very low dimensional problems. So let's just go into our mental model and say we have a 1-dimensional, you know, say growth model, as we will see in a moment. And say you discretize the one state with 10 points. So you have an upper and a lower bound, say in capital. And let's assume we cannot parallelize for the time being. Say every you know, optimization problem, if you do value function iteration, the time step would take you 1 second. So that would result in a time to solution is 10 seconds. If you have 2 dimensions and you have a Cartesian grid, you have 100 problems to solve. That would lead you to a time to solution of 1.5 minutes. So with the 1-dimensional problem, of course, you run your model, you check the result, you're not happy, you rerun it, fine. The 2-dimensional case, you run it, you go check your email, you come back, you rerun it, and then hopefully your inbox is full, otherwise you get bored very quickly. 3 dimensions, 1,000 points, takes you 15 minutes. So you go, you know, you run your code, you go and have a coffee, you come back, what you do, rerun, have another coffee. So like this is makes you very quickly very nervous for a variety of reasons. But you know, it doesn't become practical, right? And then 4 dimensions, which is still like, you know. So like the problems you're typically working with in your research, how many, you know, if you have like continuous states, how many dimensions do you work, or what did you see in grad school? Yeah. So that would be up here, but like if you go to 4, it already takes several hours, and then if you go to 10, 20, 6 would already be 1.5 weeks. So this is like a disaster if you want to finish your PhD quickly. And then 20, like this would be 3 trillion years, so it would be more than the age of the universe. So like, of course, now we could assume like this is way too long of a runtime, but even if you scale it down a few orders of magnitude, you hit the wall quite quickly. So, what can be done about that? There's a variety of lines of attack to go about this. So one is, of course, if you try to do, dimension reduction. So that means, of course, you can add expert knowledge. So saying in finance, you can often project your problem down to a simplex. So you can save 1 dimension. But there you apply your brain, but at some point you hit the limit. And then we will hear today later, for instance, from Jesus, there is also numerical techniques that exploit symmetry to implicitly project your problem down to low dimension spaces while still be able to cope with the full input state vector, which is high dimensional. So machine learning provides you a ton of ways to reduce efficiently the effective dimension. Then, what mathematicians, of course, dealt for half a century, and some of the literature is that emerged is sparse grids and related methods. So one way is to come up with functional forms that place the grids efficiently. Like you don't need to have a Cartesian grid, but a sparse grid. So you get some leeway here that can save you a few orders of magnitude. And then, of course, here, like if you did tricks here and here, you still can revert to high performance computing, which also can buy you a couple of orders of magnitude. So, like ideally, if you go across those 3 strands of attack, you're able all of a sudden to go into dimensionalities way beyond what you see here. But as I said, so here it's just the curse of dimensionality that you're facing, and you want to break or at least alleviate. What all these grid-based methods have in common is still like, even if they break the curse of dimensionality. Why? Sorry. Sorry. That's interesting. Sorry, I see something different. I'm stupid with Windows machines.
Upper left corner, it's show sidebar.
Oh, yeah, got it. Thank you.
Close all the other windows.
Okay, so this one thing is breaking or alleviating the curse of dimensionality. The other one is geometry. So like that means even if you were to use a sparse grid or something, you still waste an enormous amount of computation in regions of your problem that you really don't want to go. So what do we want to have? We want to have essentially a method that can approximate high-dimensional nonlinear functions on irregular geometries. And with irregular geometries, I mean like spheres or something. That means I want to approximate function in a grid-free way, in plain English. And this brings us now to neural nets. So yesterday I talked about training data, etc., over which you fit your functions over. So that means if you think back of the supervised learning idea, I had X and had Y. So back then it was analytical functions, but I never talked of any grid. I never talked about any geometry. It's essentially just a set of data points over which it can fit the function. And this is well, we will hear today also about another method in the third talk, but like neural nets can do that. They're agnostic about this. So what is this deep equilibrium net now doing? The key ideas, as the name said, it essentially uses neural nets to approximate policy functions, which allows to, due to the universal function approximator, in principle, approximate high-dimensional functions in strange geometries, which are, and functions can be nonlinear. But then the next thing is also what is very important. We heard yesterday that neural nets are data hungry. And now if you think back what it was just saying a few slides ago, if typically we solve to generate the data. So if I were, playing stupid, what I would do, I would have, I would draw a state X or simulate state X. And I would solve there, either a Bellman equation or a nonlinear set of equation. And then, do this, for a lot of observations, fit the neural net over. So like, I would do naive time iteration. But generating these observations is very costly. Solving a nonlinear set of equations with hundreds of variables, this is expensive. So I don't want to go there. Again, for the reason typically, a rule of thumb is if you have like d degrees of freedom in a neural net, you need at least 10 times as many data points to fit that well. So what can we do? How can we generate data cheaply for a neural net? And so what we do is essentially, I'll get more into details. The key idea is I simulate. Now, so what do I mean? So I will write down the first order conditions of the equilibrium conditions of my model. I will initialize my neural net, which represents the policies I want to approximate with random weights. So, the first order condition will never hold. And then I simulate the model. So my cost function will be the first order condition, because like by construction, they need to hold 0. I simulate the model forward. This generates me a loss, which is gigantic. I apply stochastic gradient descent. I update my policies. With updated policies, simulate the model again. Update the policies again with the neural net, etc., etc. And so this is, I mean, I go more into details, but I just want to give you first the basic idea. So that will be an unsupervised machine learning method. I don't need labels, I just simulate. The advantage of simulation is I don't need to solve every Bellman operator. I never need to solve, nonlinear set of equations. I just essentially simulate. So that means I interpolate in the neural net, from the previous iteration. This, particular with GPUs, this is so cheap, so I can generate billions of observations at no cost, update the policies, and that's it. But yeah, question. Okay, never mind. So, but this is the key idea of the thing. Now let's go into into the technical details. For the sake of time, of course, this is embedded into a large strand of literature on which you're building on, and some of the people contributing to this literature are in the room. But like, just if you want to look a bit into, how these things evolved, that's the plot. But okay, so after this lots of first, let's take a step back. So usually what you learned yesterday, so say you have a neural net and you draw parameters, and then say you have observations, you have a neural net, and then you want to minimize some cost function, right? The neural net, just to remind you, so we had some input state X, then you had these weights. So yesterday, we saw these arrows pointing to the neurons, but like in a more formal way, you have this weight matrix I plus a bias. So that would be the hidden layer 1. You know, you add, and so okay, so that's, let me go here. The input layer, then you have a nonlinear activation function that layer 1 is hidden layer 1. You know, you will go to the next set of weights. So you have here second weight matrix with parameters. Second bias that gives you hidden layer 2. Then here you have a next set of activation functions. That would be a neural net with 2 hidden layers. So just to remind you, as I just said, if you were to naively fit that, you write down like the mean square error. So if your training set D, notice again it's grid free. You know, you have your loss function, you have the observations that generate your Bellman operator, for instance, you know, the value function that you wanted to approximate, minus this, you know, flexible functional form to determine the parameters of stochastic gradient descent, the learning rate. Now, and again here is the slide that I said again. All the recursive methods that you used to, value function iteration, etc., the data generation is expensive. So you can only do it with small data. Yeah, so there's few other words I wanted to say when you do like time iteration or value function iteration. First of all, you know, if you solve a nonlinear set of equations, say you have a DSG model, and say you have you know, zero lower bound in there, and you say for, you know, bad luck, you know, you grid your falls directly on the kink of your function, and say you use as a solution method like something that is gradient based, can very well be that the solver doesn't converge, or, you know, there's all sorts of reasons why, you know, solvers cannot converge. Now this can bring you in trouble because, you know, let me actually take so say you know, say you have a polynomial of a certain order. Yeah, you would need to fit that thing. You would need to have the observations here and here, so you can solve one and two. But like here, this one cannot solve, right? And this happens in practice. You know, then you need to come up with some tricks, right? You know, like you take the functional value of the previous iteration, like you need to do all sorts of engineering. So long story that I'm telling here is, if you use these iterative methods that rely on solvers, you can run into secondary problems that do not allow you to fit functions. So I don't know, you know, Bertel and Fedor, like, do your solvers always converge?
Yes, they do.
And now, honestly, off record, I switch off the mute.
Check. You can put something that's not as expansive onto a contraction net, and then it goes everywhere.
Yes, and you know, and then the other thing is also coming back to global and local methods. If you use polynomials, so I know so for instance, Christian was working a lot with Chebyshev polynomials, for instance. So like you can also have these effects. If you do value function iteration, for instance, you know, you still want to compute the global solution to a problem. But what can happen is like you have spurious oscillations, right? So like, you know, if you change a value on some part of the state space, you know, you automatically change it, you know, the polynomial also on the other part of the state space, which is something which you really don't want to have. You want really, you know, local resolution in some sense. If you go to highly nonlinear models, as you know, climate models with well, damage functions with jump diffusion, for instance, right? Then polynomial do not apply. So neural nets, they have, you know, beyond what I said, like neural nets have this capacity to resolve local features. There's other function approximations, but they can do that. Yes.
When you're talking about parameters in context, you're talking about the weights.
Yes. Yes.
We're not talking about like coefficient of risk aversion.
No, this is Felix's job today. Yes. World champion of parameters. Yes, but more serious. Yes. So okay, so despite, you know, you have these nice properties, contraction, etc. Like if it comes to practice with you know, with sneaky models, you know, global methods, global polynomials, etc., or solving equations, non-linear set of equations or optimization problems, they can limit you in some sense.
It's true. It's true that you have to be always conscious about whether and how they converge. Two examples from yesterday is a Pauli algorithm where first you use contraction mapping feature of the Dublin operator before switching to Newton control. Another example is using well thought through starting values, as I was mentioning in the last paper.
So we have the neural net, which has these nice properties. But as I said, now the key insight is now, how do you choose a loss function that allows you to train your economy, you know, your neural net that represents the solution to your model, like computes equilibria. The basic idea is really, so we know the equilibrium conditions of the models, right? So we can write down, well, the derivatives. You know, if you take your value function, as we will do in a moment, you take the first order conditions, blah 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 blah. You know, so in an ORG model, typically agents maximize, firms maximize, markets clear. You know, the usual thing. So you know the first order. So we use that in the following sense. So assume we knew, and forget about multiple equilibria for the time being, but just assume we knew the true equilibrium policies. So I represent them as G for the time being. And say F would be my equilibrium policy. Then I would know if I simulate my model, so X would be my state. I simulate my, you know, somehow, you know, say I start somewhere and I simulate it somehow. Along the simulated path, this would hold. And so numerically that would approximately hold, right? But now the question is, how can I get there? And as I said, so now let's, in abstract way, then you get more concrete. So I represent my policies with the neural net. So I would have something here. Here I would have like my economic states. Then I have here, you know, the hidden layers. Then say I have here like as a policy, you know, say capital tomorrow. So if I write down my first condition, this will be my loss function. Now what I do, I use this as a loss function, initialize my neural net. So all the coefficients here W1, W2, W3. I initialize these weight matrices randomly, as we always do. We heard yesterday there's a bunch of ways to initialize the neural net weights. But this means I have here like a super crappy policy, but it's a guess. It's really a bad guess, but it's a guess. I can do that. But now, let me simulate. So as I said, I take a state X. I typically have a law of motion to get from a law of motion to get from state t to t plus 1. So at state here, evaluate g. I'm being sloppy here a bit. So evaluate. Then I take xt plus 1. Evaluate the loss function again. So I do this say for 10,000 steps. This will be my loss function. And as I said, because I initialize my neural net randomly, this loss will be gigantic. Will be say of order 10 to the, sometimes 10 to the 10 or whatever. It's just like gigantic, but I don't care. Then once I have data collected, and as I said, the simulation is so cheap. Based on that, I update the neural net. So like I do backpropagation, update the weights. With the new weights, I repeat the game. I simulate again, say 10,000 steps forward. The policy will be slightly improved. I simulate again. Policy will be slightly improved. And so there's two things, and you will see the moment. One is the model automatically will focus in part of the state space where the simulation, so the model lives where the simulation is. So by construction, you only have a fit to you solve the model where it lives. So like, if you have the simulation thing, and say once, I will come to the convergence criteria later, but like say that convergence, if you simulate a model, this looks like this. I have a fit then just on that sphere. I don't need to solve anything out there. Is that sort of clear? Yes? Can you speak a bit louder?
So yeah, especially since we're bootstrapping the data by iterating the networks, why don't we want to pick up principal initialization of the figure 1 over 1 minus beta?
I mean, look, so you're of course right. It's always like if you start with a good guess, you converge faster. Of course, like there's a bunch of stuff that I ignored, but like, I mean, you're completely right. Like if you, I mean, this is also more in the sense of pre-training, right? So for instance, what you could try, for me it never worked, but I know for us. So like, say you have a complex model, you could take Dynar, you take the second order approximation, so you have a rough guess for your solution. Then you fit the neural net to that, then you release it. So I mean, you're absolutely right. Luckily it works most of the time without that. But you're right. The more you help, the more you steer, the quicker it converges. And we will do that actually in the example today too. So instead of approximating capital tomorrow as a policy, we will use the savings rate, which is something a value between 0 and 1. Then you take the sigmoid activation function. So it's much easier to get it converge. But yeah, so the basic idea is still like just initialize your model, simulate. You don't need to solve nonlinear sets of equations. With an equation solver, you don't need to, do the supervised learning. You just simulate, update weights, simulate, update weights, etc.
Sorry.
Yes?
Just to understand, so for the older guys in the room, so in a sense, this is like an equation solver approach, like the old days.
It's close to, like when you think of the methods by, yeah, exactly. It's just like function approximation is fancy.
Exactly. Okay.
Yes.
Simon,
yes.
Question. So we initialize with somehow, right? And the first steps, especially the policy that we use for simulation is really bad.
Yes.
Is there any concern that, with those simulations, you may end up in the wrong part of the state space?
Yes, I mean, yes, so-
Convergence together of the neural net and the part of the state space where you want to solve it.
Yes, I mean, sure. So like, for instance, one thing is if you have multiple equilibria. So I once tried to solve a DSG model with 2 equilibria. But I didn't know, I was told it has only 1, but it turned out it had 2. So I learned the hard way. But so you solve somewhere, and then you jump somewhere else. But this is a good point. Like what we will do today, of course, you can also just say the simulation is very efficient. For this type of thing, you can of course also exogenously sample, continue to exogenously sample, like in a Monte Carlo style, and then just fit the function over that and still use the simulation approach. This also works. And then the other thing with initialization is, of course, like but just for the training purposes, you could end up with infeasible policies or stuff like that. But this you can fix, for instance, with choosing your neural network architecture cleverly. So what I was just saying. So for instance, if you, in the output layer, if you use like you choose your policy to be the savings rate and you use sigmoid, and just by construction, yes, or like in OLG model, when you have KKT multiplier, you use a soft plus activation. I know John hates this expression, but if you use a soft plus by construction, like it will be positive. Yes.
We ran into this problem and we had to add a little hack around it. Just having to call back to basically resimulate, like to reset the data in batches after the neural network update. So this wasn't
Okay. Yes, sorry.
So, as I understand here, it's a layer that you can use for this optimization problem, right? But if the environment, say, have some stochastic element to return, right? So you imagine you take a step and then you get some reward from the environment. Is there some? Could you then imagine that the marginal utility in both periods is not the same from consumption, because you get like a boost to your like income in the next period, for example? Like is that underlying some idea of you simulate so much that you kind of integrate out in the stochastic?
Yeah, this we will do. I mean, I'm not fully sure if I understood you correctly, but like if you have stochastic processes in there, like of course, like if you think of your value function is like V equal max U plus expectation, blah blah blah. V prime. This works, and we will do that. But if you have something different in mind, I don't know.
Yeah. My point is, we just simulate, right?
Yeah, but at each, of course, like at each point where you have the simulation, you need to evaluate this expectation, and this will be some sort of costly, of course. So like that's why you either need to resort to Monte Carlo with few points, or to like a quadrature rule, which has like scales nicely with dimensions. So like if you have like normally distribute just like a monomial rule that scales linearly with dimension, or something that only scales in square power, but not like you don't want to build a dense grid, because this would kill you again. But in the notebooks, you will see that in the second notebook. But like just to come back, this is a very general or like very well, it looks simple, but essentially you can engineer your cost function as much as you want, as long as here you get 0 out. If you want other terms like calibrate some parameters or whatever, you can stick that in. If you want to match moments, say you want to have like a model that matches, I don't know, that to GDP, because you simulate, can track that or GDP across the simulated way. So you can have this empirical part minus the observed part, and you add that there. So you force the model into something. You just need to construct a loss function where you can generate data by simulating, and again, you can be creative about that. Yes.
So I think for like many economic models, we have different ways to write down equilibrium conditions. Do you have any thoughts about which particular equilibrium condition would kind of the loss function here, we usually want to pick.
So now you bring me in trouble because like my co-author Marlon Acinovic and I have completely different views on that. At this point in time, I would like to avoid your question. Like some people like to work more with the Euler equations. Well, this is a dinner discussion. So.
Let me point something out. Coming up with a function G is not specific to machine learning.
Yeah.
So this is a problem for the discussion that holds, even if you were solving this with it's a polynomial.
Yeah, exactly. Yeah, so like Wouter and Hahn, like 30 years ago or something, was the same approach, yes.
No, I mentioned that because I often get this type of questions in my seminars, and I just want people to understand what is a question that holds for any numerical approximation method. This is a question that is specific to the
Yes.
Your G function, can that be as well the Bellman equation itself, or any first-order condition of the maximization step? And which one would be better, or do you want?
Let me get to the examples. Let me get to the examples. As I said, so you mean essentially you want to take the Bellman operator left hand minus right hand side.
Yeah.
And then so there is some papers actually. I haven't put them to the top of this. Some papers from Google that show. I mean, theoretically you're right, but there's some papers recently that show that leads to bad results. So this is poor answer, I know, but theoretically you're right. Practically, there's work that shows you rather work with first order conditions. But actually, good point. Please remind me. I'll upload that to the readings list. So let me because I really want to keep the time. Let me just again quickly. I know it's a bit small. Just remind you of the algorithm. So it's initialize. So like choose the network architecture. So this is something you need to do. Like there's no good. Well, it's just try and error, unfortunately. In contrast to like people working in convolutional neural networks, so in Econ still a lot of try and error. But yeah, I mean, you can go to some of the papers out there and see what the network architecture is, and then start from there. Basic idea is really you should use activation functions that scale, so avoid the exploding gradient sort of thing, or diminish vanishing gradient sort of issues. But anyway, so you initialize a neural net somehow, including the weights. You pick a point in the state space which you deem feasible, or as we discussed, choose, for instance, from a non-stochastic model, steady state, and then you start to simulate. Along the simulation path, you evaluate, you generate the loss function, you update the weights, and you continue until convergence. And now convergence is, of course, again, in the eye of the beholder, right? So if you work with the, we will do relative, so I will give you in a moment, we'll give you a loss function which is essentially percentage error loss in consumption. So data loss has a concrete interpretation. But if you work with very rich models, where you have like all sorts of different parts of your model contributing to the loss function, sometimes interpreting the loss economically may be hard. So I cannot, similar to my pesky question yesterday to John Stakersky, like if I tell you now 10 to the negative 4 error is good, you need to do a lot of robustness to make sure when you claim victory that you solved your model, that it's actually good. So you may want to run your model a little longer, say half an order of magnitude more or 1 order of magnitude lower. Then you see if the policy changes. And another thing, well, I stop here otherwise. But you see, it's just you need to carefully think about what your loss means in economic terms and what is satisfying, and you need to do robustness checks. You know, you don't want to get into the situation where you write the job market paper, you solve your model, and then if you solve it for half an order of magnitude more, you know, your results do not hold anymore. There was just recently the case, famous paper in American Economic Review, you know, highly cited. And then there were some people from the Fed, they showed, and it was in one of the top finance papers, and then some people from the Fed showed if you solve it more accurately, nothing holds. So you don't want to go there if you can.
It seems to be the number of time periods, but like, what does it happen? You're saying that there's a number of epochs in each episode. What is that?
So say you have, you know, think of the say you simulate kind of effects.
It's what we discussed yesterday in computing the derivative from the parts of the standard observations. And once you've computed the derivatives for all of the observations, you complete the effort.
Yes. Okay, now let's quickly show about look at two notebooks, and again, like I will go. Yes.
Sorry, I just had one conceptual question on the loss function, and that is, if I understand it right, then you know we could have like the value function, whole set of policy functions as individual components of the loss function, and then just do some norm on those to get our overall G function. And so do you have a neural net with one output? Do you have a neural net with multiple outputs? And why? Right. So the question is, why approximate, if you want, everything in this very high dimensional network, and why not have a separate neural net, like I would use a separate polynomial that approximates each policy function? Why not have a separate neural net for each of these tasks?
That would be super complicated to train. I mean, you think of it like then you have essentially a loop.
Yeah.
Or,
well, you
I mean, look, you know what you're telling me. You know, this may work, of course, but like I said, it's just super intricate. But that would be.
It's just curiosity, right? I'm just trying to understand, because you know I grew up with always trying to minimize complexity, right? And in a sense,
so
this the full connection.
Yeah, I mean, you know, the architect, as I said, you can choose, like you could,
okay.
But I mean, later today we'll also hear about symmetries and stuff.
Can I?
Yeah, sure, feel free.
Okay. So you need to reformat the fabric. That's the best way. Then you know, burn it down and go to Amazon and get it. We are able these days to solve neural networks with 1 trillion parameters. Trillion, not billion. You know, billion is for babies. It's like, you know, for no, we're not very smart. Okay, so we can solve things with 1 trillion. It's okay. I have been on the record many times. So since the faculty the lab. But anyway. The point over here is the optimizers like Adam, and the fact that you can flash all these things in the GPU is so powerful that any type of quote-unquote thinking, like let me have a neural network for this and another neural network for this, and do something slightly different over here to gain a little bit of gain, is going to be defeated by a pure engineering force. Okay, just do 1 trillion parameters and you know, let Python figure it out how to do it. Don't waste your time.
Yeah, so he can say that. But you know, I don't have time to get it, but like this would be, for instance, an OLG model, as I said, like, you know, annually calibrated. It doesn't have a billion parameters, it has like a 40 million parameters. You run it on a laptop in a few minutes. Well, you know, let me just quickly go and so sorry for being a bit short here. So the first notebook, let me quickly launch. So the first notebook, as I said, it's just purely, show you the mechanics, how you can do that. This is, as we heard, there's multiple ways of doing that, but the first notebook is essentially, you have this growth model by Brook and Meerman. If you, put full depreciation, it has an analytical solution. So if you have you maximize utility, log utility, so we have here consumption subject to the budget constraints, and you have output-wise k to the power of alpha. Now let's just, I need to swap the screen. Let me go over here. So that's. Oh, sorry, I'm still on the wrong. That's the one. Sorry.
You press a little X on the top of the screen.
Yeah.
Just has an code caption.
So I have here this first model. Again, here describes what we do. Now you write down, so I'm not going through all the details here, but you write down Bernoulli equation, then you plug in the budget constraint, you do the usual, so like in principle what you wanted to do, like the state variable is k today. What you would want to approximate with the neural net is k tomorrow. Then we derive the first order conditions. And so the cost function that we want to have is here, this relative consumption error, right? So that would be the thing. I'm not going through all of that, you can do that later. This is the G. The input X would be K. The right hand side of the neural net would be KT plus 1 that you want to approximate. And now, so this is of course, to start with, let's make it simple. So it's a non-stochastic model. So instead of simulating the model, I have K lower bar and K, well, actually, it's written there, but like you have K upper bar, K lower bar. From this range, I sample uniformly. I mean, you could also put up a grid at this point, but like we just add all of these Ks, different Ks. We evaluate the cost function. We update the neural net. We draw again. We plug that into the neural net. We draw again. So you will see it here. Blah blah blah. So I choose the parameters. Sorry. So first, I import TensorFlow. You can do that yourself with any other neural net library on your liking. So I have here alpha, beta, delta. I put to 1 because I have the analytical solution, but you can put it to more reasonable values, of course. Then here I have my analytical solutions. So let's go with that quickly. Now what I would do this one thing. So in principle, as I said, and this was discussed earlier, so like if you initialize your neural net randomly, sometimes you can have like infeasible policies which cause you trouble. So you may want to hard code expert knowledge into the network architecture. So instead of choosing capital tomorrow as a policy function, I can have an equivalent. This will be the savings rate, which is of course between 0 and 1. So this is, formally I would want to have policy tomorrow, so the policy would pay my capital tomorrow, but this can cause me some numerical trouble. So what I will do is I will use the savings. And now, so what that would mean, so here instead of having KT plus 1, I have the savings, which is between 0 and 1. And now to make sure that you don't get into numerical trouble, because like if I initialize that thing randomly, it could cause me, as I said, headaches. So I use an activation function here, the sigmoid on the output layer. So this by construction puts me between 0 and 1. And this is just like a general trick that applies. So also like if you work with models, where you have KKT multipliers, so you need to carry, or like large multipliers in general, they need to be, you can enforce them by using a soft plus activation function. So you don't run into these troubles. As I mentioned, if you have a numerical gradient-based solver, you can run into trouble. Here you don't. If you use your brain and choose, well, the policies or the network architecture in appropriate fashion. So anyway, let me go through that. So we choose here the network architecture. Okay, so it's a complete overdoing. One input, 2 hidden layers with 50 neurons each, 1 output layer. Now let me step through that. So here it's all, the detailed explanation is also in the notebook, the introduction notebook I handed out to you yesterday. So we have like here the hidden layers. So I do relo activation. And notice again here, the output layer is sigmoid activated. Then, so, you can see how many parameters you have in that network. So just to show that what you can. Now we sample from, here we define the post function. Let me skip through. Then we sample now the data, as I said, because it's non-stochastic, for a given set of parameters, the true solution, but we do that for an entire range. Now I train the network, and you see, very quickly the loss goes down to, so this is, percentage in consumption error. So it quickly goes to 10 to the negative 8 loss function. Consumption error. So this thing converges, clearly, because it's a trivial problem, it converges extremely quickly to very low values, high accuracy. So like here we plot true solution against the numerical solution. So, but this is again just mechanically to see how. Yes.
So when you train your neural net, like you also update them, you're setting the number of layers and activation function, or you only update weights?
Yes, only the weights.
Then how do you know whether the weights or not? Like we have to try.
Yes, so that's this is one of my favorite jokes. It's like it's called student gradient descent. So like using or trying different neural network architectures, this can be cumbersome. And I think half of your PhD was essentially searching for neural network architectures. So no, it's a good question. This is finding a good neural network architecture can take time. So I mean, also I don't know how much time you spent on. You spend probably more time on finding this one than once you have it. These things they solve in no time. But sometimes. Sorry for that, I don't give you a good answer here, but you need to try essentially a batch of architecture. Then one of my former PhD students actually, I had a grant on the National Swiss Supercomputing Center, and he created a batch for this. So 90 essentially burned of order, 4,000 node hours on the GPU to find. This was costly, I tell you. So,
is there any rule of thumb, like, you need to avoid at least too few layers and too long?
No, I mean, look, so I mean, okay, if you, so as a rule of thumb is essentially, but this from the literature, of course, like the deeper you go, so like theoretically, one hidden layer, with a lot of nodes that should be able to approximate pretty much everything, but what happens in practice, like people go to deeper and deeper networks with relatively few nodes, and this implies then you need to choose activation functions accordingly in the hidden layers. So like, it's relu, it's celu, or like swish. So but again, if you never worked with that, I would go to the published papers a bit and see what the architectures they choose, because they're often relatively different, not different, but similar. But I mean that there hasn't been too many publications. What do you use in your papers?
Silent architecture.
Yes. So what about activation functions?
Oh, activation functions. So in the paper Econometric, I will have a soft class, and in the paper I will present later today we have a use. So, but again, this goes a little bit to the point I was making before, and I think there is a session on double descent phenomenon.
Yes.
So basically, the double descent phenomenon. Another way to say it is stop worrying about over-parameterization and start modeling it. In case of doubt, over-parameterization. But parameterization is not an issue over here. So basically, I'm not sure if I should have 4 layers or 8 layers.
Yeah, but it's a problem. So like also if you look at these large language models and you see the learning schedule, like they also, I mean, there's many more things. Like sometimes, like you manually need to intervene in the learning and restart and do. But again, so like if you start to do, I don't know what you have in mind, but like if you start to work with solving models and you go say from a 2-dimensional model to 5 or something, this is dirt cheap to do. Like the stuff I'm talking about that really gives you a headache if you go to hundreds of state variables, then it becomes also a bit hard to debug because you need to monitor. You can imagine like if you have an orgy model, like things go south, you need to essentially look at all the outputs, what's going wrong, and then you need to go back to the problem. But like with few policies, relatively few states, just more than what we were able to do before.
So
just hard.
You guys in some of the sessions I may have you show them the playground by TensorFlow.
Yes, yesterday.
That's kind of a very nice way.
Yes, so this is all there. But okay, let me just, because I want to be on time today. So there's a second notebook, same model. With this, sorry, so same model as before with a slight twist. You have stochastic shocks to productivity. So that means instead of having the LNC, you have the expectation to compute. So what we will do is, and again you can do it slowly, again derive the loss function. It looks like this. So the only difference here is this expectation operator. And as I said, unfortunately, at least with our method, this thing you need to numerically evaluate. So that means every integral numerically is a sum. And so what we do is essentially here in the simple example, let me jump there. So we use Gauss-Hermite, so it's not too bad. So like here you see the quadrature nodes that you have. So essentially instead of having a continuous integral, it's a weighted sum of the function evaluated with some weight, given here with the nodes and the weights. So like when I simulate my loss at a given state, essentially evaluate at x, fx, then I have these extra states I need to evaluate, I compute the sum, and then move on. So like essentially, if you forget about the optimization procedure, so loosely speaking, here my generation of data, generation of data goes 5 times longer because like it's x, like values, next x, values, etc. So it becomes like if you have expectations, things become more expensive. That's why this, if you have like continuous shocks, this can become a bit more costly. But again, since we simulate, we can simulate billions of observations in no time. In a minute, I will also show you can do that in parallel. So that's the nice thing. Simulation is completely parallelizable. Okay, but let me just quickly step through that. Again, we have this loss function, the parameters, the quadrature rules. We run that. So the training will take here a little bit longer. So I'm stepping through all of that. And then what we do is two things. Again, like so first, just for pedagogical reasons, we will sample exogenously. Essentially still have the two-dimensional cube, fit the function over that, because it's, we can do that. To solve that, so this thing will converge. It converges, nicely and closely. Like it converges, of course, slower than before, but it converges. But what I wanted to bring us at in the last part is now, since we have simulations, this is going down, down, down. So here with the simulation, so this is, if I simulate my model, this is how it looks like. And so instead of now sampling from this entire, two-dimensional domain, I sample and I fit my neural net. So that would be the, the ergodic distribution, right? So I never fit the function here, never function here. So you see already, just by the intuition, I focus the resources where they are needed. So if you say you have a budget for training data, essentially only generate them where you need them. Or you can argue alternatively, here you just need half of the training data essentially to have a good fit. Or in the d-dimensional case, you again like 1/d factorial of data you save. So like it's quite nicely. So I let you play with that and go back to a few more comments. So that's the presentation. So, to pull a bigger wagon, it's easier to grow, to add more oxen than to grow gigantic ox, right? So what do I mean with that? So it's, when I was a PhD student a long time ago, this was a book in MPI, so methods passing into, I liked it a lot, but you guys don't need to do that anymore. So to come back to the question of, if you have like quadrature, like you need more data. And the nice thing is when you have simulation or like generally just, our data generating process, we know it. And, we can use computers. So like, instead of having one GPU, which already can do a lot, we can use multiple of those. So what I showed you before is trivially parallelizable. So essentially, and this is, it's not my invention, this is Hollywood. It's actually a product originally by Uber engineers. So that's also what I meant, like the entire world works in this sort of technology. This, you don't need to reinvent the wheel, you just need to engineer things together to solve your problem at hand. So assume I know a policy. I can, of course, copy this policy on multiple GPUs with a different seed, random seed, and simulate forward. So if I need to, sample 1 billion points, I don't need to sample them on a single device. I can sample them on 10 devices, right? So you split up the work. This is what I do here. So like if you have n devices and you have like a size of simulation that you want to have n, so you generate a subset n, you split them with MPI in different computing units, you simulate, you compute locally the gradient, then you do an all-gather operation. So like essentially average over all the gradients. It's in the spirit of the stochastic gradient, of course. You update the policy, you distribute the policy across the different compute units, and you repeat that. So we did that, and you can imagine this is trivially parallelizable, so you have almost no overhead. So in this example, you could scale up to 500 GPUs. I mean, it was completely, with almost, so like ideal scaling, those of you who do a bit supercomputing, like, if you have a problem size and, a problem that takes on 1 second to solve on 1 unit, if you have 2 units, you would have 0.5 in ideal world. But you have always some overhead, right? You need to copy data around, so like, it's in sort of a diminishing rate of return. But since here, you spend most of the time computing and almost no time communicating, you can really push this approach down. So like, when you show that to a supercomputing guy, they will be super happy. That's almost perfect scaling up to 500 GPUs. And so this was the example of a it's a relatively simple OLG model that's just like solved 500 times faster. If you have like a crazy model, I mean, of course, you need to get a grant or money to pay those resources. But I'm just saying, the neural net part gets you very far. I mean, if you have like something absurdly complicated, you can brute force it to that, because like also like the structure of the problem is such that you can nicely parallelize this with some problems in econ. For instance, also the nested fixed point thing, you have limits on parallelization. You need to solve to the algebra bin. Here you don't. It's just like boom. It's just throw gigantic sample size at many devices and then do a reduction in the end. Yes.
Quick question: does the sample size, this increases exponentially, right? If you would have to increase that, if the problem size get bigger, the number of samples you increase as well?
I think that's. I would formulate it differently. So sometimes if you have a very big problem, of course you need to have a lot of data, because like say you have a big neural net has a lot of parameters, you need a lot of data. And to produce a lot of data, at some point it becomes in any way costly, right? But this is trivially parallelizable. That's what I would say. So if you have like your trillion parameters, you may want to have multiple trillions of observations along the way. Yes, and then of course, yes. Oh no, just one second. And so this was, you have all these codes, the notebooks, they're not tuned. We use this, like this approach in all sorts of things. So Felix will talk more about climate economics and uncertainty quantification there. So we have, here, this is a bit of a cumbersome code, but you can also find that on GitHub, where you can solve non-stationary models. So like here, it's in the context of climate change. But so we talked about non-stationarity. The logic, if you look at the paper in the appendix, applies. So we derive there how you design a cost function with non-stationarity. Download it, play with it. Yeah. So the presentation, as I said, so this next part is just like more add-on material. But I think I stop here. And if you have more questions, discuss them over lunch.
So there's a question online very quickly from Yulang John. Would you normalize input before taking it into the neural net?
Yes.
And it was quick.
Yes.
You can come back and do it.
Yes. Okay. Yes. Okay. Then thanks. And then next one is then Yucheng. Now we had a lot of state variables. And now he's going into heterogeneous agent type of things. So thanks for your attention.